All right, now let's take a few moments and think critically about what we've learned about standard deviation so far. So we've learned that you have to use the units of measure are the same as those of the original data values. So the set we had before, we were looking at the weight in kilograms. You report both the mean in kilograms and also the standard deviation in kilograms. Standard deviation should never be negative because, again, we're squaring them and then take the square root. So if somehow you're getting a negative standard deviation, you have clearly done something wrong. You need to stop and go back. Now, let's look at our third point. So if I have a larger value of standard deviation, what does that indicate about the amount of variation in my data set? Think about this for a moment, and then when you've got the answer, move on to the next slide. It's going to be a larger amount of variation. So the larger standard deviation means greater variation around my mean. All right. Now, last thing we're going to look at is that the standard deviation is in fact very sensitive to outliers. So to get an idea of what that looks like, let's work with some sample data again. So we've got our information here from the class pulse rate on the left. And here on the right, I've gone through and calculated for you the same information if I've added in the unusual data value of 158. So again, 158 is our student who has stage 2 hypertension, okay? Notice this changed my standard deviation a lot. So I went from a standard deviation of 4.8, which is pretty reasonable, to a standard deviation of 20.1. That tells me that with that single pulse rate added in, that has really increased the spread of my distribution, and it's undercut the accuracy of my mean in being able to predict future values, okay? So that's what that means, larger variation. Notice then when we look at the boundaries for the one standard deviation points, we can see that for the second set where we have the 158 added in, they're much wider. We see that all the way down for each level of the standard deviations, from 1 standard deviation, 2 standard deviations, and 3 standard deviations. So let's take a look at this. Notice that all the data values in our first set of class pulse rates are within 3 standard deviations, okay? However, when we're looking at our addition of a person with stage 2 hypertension, we can see that their data value, 158, is still outside 3 standard deviations, even though the range has gotten much broader. So, is 158 an unusual pulse rate for the class? Yes, it's outside the 2 standard deviations. So, again, this is where we're applying our estimates of 2 standard deviations to be able to make a statement about particular data points. Notice, when we're looking at this, and we apply the empirical rule, our empirical rule says that at 3 standard deviations, we should have 99.7% of all of our data values. And in fact, we have 100% of our data values. However, when we apply the empirical rule to our other set with the additional individual with a pulse rate of 158, applying the empirical rule leads to an inaccurate prediction. So again, the empirical rule says we should have 99.7% within 3 standard deviations, but we in fact only have 95.2%. So this is an inaccurate estimate. Let's take a look at what's producing this problem. The problem, in order to do this, we need to look at histograms. So here I've made 2 histograms for us to compare. On the left, we have the histogram of the pulse rates from the class. And we can see not quite a normal distribution, but it's pretty close. And then we see over here on the right, this is the histogram with the additional hypertension pulse rate added in. And we can see that it is a very strongly rightly skewed distribution. That one single pulse rate is pulling everything over. So if we drew our distribution curve, it would be coming up and peaking at around 72 and then dropping off down to 158. Okay, so that is not the shape of a normal distribution. It is a non-normal distribution. This is why we applying the empirical rule to our second set here with the additional 158 pulse rate produces an inaccurate estimate. It's because we're using the empirical rule, which can only be used for a normal distribution. And so when we're looking at this, we have a non-normal distribution, such as a particular example. How do we make some accurate estimates about it? Well, to do that, we're going to use Chebyshev's theorem. So Chebyshev's theorem is applied to non-normal distributions. So when we're looking at this, Chebyshev's theorem says that we should have 75% of the class pulse rate data within 2 standard deviations of the mean, and at least 88.89% within 3 standard deviations of the mean. Okay, now notice a couple of things about Chebyshev's theorem. Again, you can see here the shape for the distribution is non-normal. Okay, is some variation from normal in some manner. Notice also Chebyshev's does not make any predictions about values within 1 standard deviation. It only looks at 2 standard deviations and 3 standard deviations. Okay, so let's use Chebyshev's theorem and see how this matches up with our data. So here we have our 2 standard deviations. I've gone through and added them into our chart here. And when we go through and look at our frequency of our pulse rates from our data set, we can see that 20 of them fit within 2 standard deviations and 20 of them fit within 3 standard deviations. Now our total number is 21. So when we take 20 divided by 21 and then times it by 100, we find that 95% of our pulse rates for the second data set fall within 2 standard deviations, and again 95 are falling within 3 standard deviations. So when we're looking at this, we can see that using the Chebyshev's theorem allows us to make a more accurate prediction for what we're looking at when we have outliers in our data set. So Chebyshev's theorem, although not nearly as specific and exact in our expectations, allows us to get more accurate predictions. So in real life, lots of data you're going to deal with has a non-normal distribution, and in those cases, you're going to need Chebyshev's theorem to be able to make some expectations and predictions about your data. So keep in mind here, again, we see that using our data actually comes in at 95% at 3 standard deviations, which is a larger amount encompassed in the 3 standard deviations than that predicted by Chebyshev's theorem. However, whenever we are making decisions in statistics, we err on the side of caution. So that means we select the more conservative option. So we would rather select the option given by Chebyshev's theorem, which is more conservative, than selecting the option that was offered by the empirical theorem, the empirical rule theorem, because it actually overestimates what we would likely to get. So when in doubt, we want to make underestimates in these situations. So this concludes our discussion of Chebyshev's theorem and its application. The next step we have is going to be looking at differences in the formulas for doing a standard deviation for a sample and for population.